So in this video, we're just going to demonstrate how to prove that a transformation is a linear transformation. And so the key is when we're proving that a transformation, here I'm given a transformation, t sends the vector xy to the vector minus x minus y comma twice x. So this is a two-component vector getting sent to a two-component vector. So our transformation is actually a transformation from R2 to R2. And what we need to show is that that transformation right here meets each of these two criteria. These were the criteria that defined the linear transformation. So to do this, we need three things. We need a vector u, a vector v, and a scalar c. And the two vectors have to be vectors in R2 because the transformation wants vectors in R2 and that maps them to a vector in R2. So to start the proof, that's what you would do. First, you'd create the things that you need for the to demonstrate that we have a linear transformation. So you'd start off by saying let u, which will give components u sub 1 and u sub 2. These need to be arbitrary vectors. So here's one vector in R2. Here's another vector in R2, v sub 1, v sub 2. And we'll let c be a scalar, which means c needs to be an element of the real numbers. So first we want to demonstrate that this is true. We want to demonstrate that if we add the vectors first and then transform them, we get the same thing as if we transform the vectors and then add them. So we'll do that. So we'll say now note that let's transform our two vectors. So apply the transformation to the sum of the two vectors. So apply it to the sum of the two vectors. Transformation applied to the sum of u and v, which is the same as the transformation applied to, let's take the sum of u and v. So the sum u plus v is going to be u sub 1 plus v sub 1 in its first component, comma, and it's going to have u sub 2 and v sub 2 as its second component. Use vector notation there. Let's go ahead and apply the transformation to the vector that is the sum of u and v. So the transformation says negate, create a vector by negating the x coordinate. So negate the x coordinate, u1 plus v1, minus the y coordinate. The y coordinate is u2 plus v2. And then that finishes component 1. Component 2 says take and double the x component. So double u1 plus v1, twice u1 plus v1. So there's the transform vector. And now notice that we can distribute the minus signs and distribute the 2. So we get minus u1 minus v1 minus u2 minus v sub 2, comma, twice u1 plus twice v1. And now what we can do is pull the components apart. Pull the u's out into one vector, pull the v's out into another. So this is the same. This vector here is the same as minus u1 minus u2, comma, twice u1 from here, plus the vector minus v1 minus v2 in the first component, comma, second component, twice v sub 1. And what you want to do is take a moment to look at these two and recognize that if we add them together, we'll get back the previous line. Equals, and what we want to notice here is that this is exactly what we would get if we applied this transformation t directly to the vector u. So this first vector right here is just the transformation applied to vector u, plus the second vector right here is exactly what we would get if we directly applied the transformation to the vector v. So property 1 for linear transformations holds. We get the same result if we add first and then transform as if we transform first and then add. Now, note that. Now let's apply the transformation to a scaled version of u. So now note that the transformation applied to c times u, which is just the transformation applied to the vector, distribute c into the vector using our definition of scalar multiplication. So this is going to be c times u sub 1 plus c times u sub 1, comma, c times u sub 2, distributing c into our vector u, equals, now apply the transformation to this vector. So if we do that, up here we do the opposite of the x component, so minus c u sub 1, minus the y component, so minus c u sub 2, comma, and then the second component we double the x component, so twice c u sub 1. So there's our transformed vector. And notice that we can factor the c out of this. So the c, which is just a scalar, could be factored out, which would leave us minus u sub 1 minus u sub 2, comma, twice u sub 1, which is actually just c applied to the transformed u. So we meet criteria 2. I hope this isn't down on my face. I hope my face is down here. We'll see when we play the video back. So then we can come to our conclusion, because addition and scalar multiplication, because addition and scalar multiplication were preserved by our transformation t, by t, that's this guy here, that's his name, by t. T is a linear transformation, which is what we wanted to prove. And that ends the proof.